This video continues where the distillation column basics video left off, and if you recall, we have a feed that is made up of 3 components. We would like to split off the propane from the other 2 components and design a distillation column to do this. We built a shortcut distillation column, and then based on the information provided by the performance tab of the shortcut distillation column, we were able to go ahead and design a distillation column model, or build a distillation column model that was fairly easy to solve because we had used good initial estimates. At this point, I'll delete the shortcut distillation column model, and we will make this the focus of our continued work. Excuse me. Okay, in this column we had the feed come in. We specified 10 stages, and these would be 10 ideal stages. We were able to find at the top that the composition was nearly all propane, and at the bottom there was nearly no propane. However, the temperature of the top is 5.474. Now, whilst we may like the fact that we have such great separation of the propane, we would need a refrigerant to reach these temperatures. In this case, we would like to not have to use a refrigerant, and we would like to see what is the highest temperature we can use and still get the separation of propane that we require. To do this, we take a closer look at the distillation column form, and you can see that there is a monitor page which tells you how close your distillation column is to solving, gives you summary information on specifications. Also, you can see a temperature profile for the column. The spec sheet gives us information on what has been specified or what constraints have been placed on the column. For our case, we had a reflux ratio of 2, and that is an active spec. Our overhead vapor rate of 550 kilogram moles with an active spec. Note, the reflux rate is not an active spec, neither is the bottoms product rate. They do not contribute to the calculation other than to provide estimates. You can also select to remove them as estimates, or in fact remove them altogether from the list. Note, your distillation column is still solved because your degrees of freedom are still 0 and you are still at a solution. Now, we may want to add a specification, or we want to add a specification such that the top of the column is allowed to continue to produce high quality propane but to raise the temperature. What we can do is we can add a specification, and we can add the column component fraction specification, and we will specify that in the reboiler, because we want to ensure that very little propane is lost there, we will have a mole fraction in the liquid of component propane of roughly 3%, but we won't put that value in because we know we don't need an active spec at this point. However, we can see that when we select the component fraction spec we created, even though it's not active, we have a value that has been calculated. The other spec we can add is a column component, a column temperature. In this case, the temperature we're most interested in is the condenser temperature. Here we can see that the column temperature is 5.474. What we're going to do next is we're going to free up one of the variables, which is the overhead vapor rate, and we are going to transfer that spec onto the temperature spec. So what we'll do first is type in the temperature that we see as the calculated value, which will ensure that our column will solve when we transfer to this specification. We can then deactivate the overhead vapor rate and know that your column is now under specified. Go to the temperature and activate that. Your column will solve. We have not really changed anything in the calculation matrix. We have actually just shifted which variable it will solve. Now we can attempt to raise the temperature and see the effects on our component fraction whilst holding our reflux ratio at 2. So if we were to do 8 degrees Celsius, we may have to stop, reset, and rerun our column, and we would get a solution at 8 degrees Celsius. We can continue this, slowly bringing the temperature up to where we want it to be. Note the component mole fraction of propane in the bottoms is decreasing, but in a similar way we can see that the overhead rate is increasing. However, we are going to see a higher content of heavier hydrocarbons in the TOPS product. We can verify that here. Now we have a slightly higher I-pentane composition. We can, of course, increase the reflux ratio in an attempt to reduce the heavier hydrocarbon component. And we can see that we were able to solve. Now we will add, just so that we can quickly look at it, column component fraction. In the condenser of component I-pentane, and again we're not going to activate that spec, we're just going to look at it, and here we can see that we have a very, very small fraction of I-pentane present. We can continue to raise the temperature, of course being mindful that we may reach a point where a solution is no longer valid. We would like to get this temperature up to about 30 degrees. At 30 degrees we can use cooling water to perform the condenser cooling operation. And now we can look at, for a reflux ratio of 4, the overhead vapor rate is 623 kilograms per second, and the propane in the bottoms is very, very small. However, we will see that the propane in the top, the I-pentane in the top, has actually increased significantly. Here you can see 88% propane, 11% I-pentane. Now, what you can do is you can send this to a second column to try to separate the two components. We can also look at a case study of how the reflux ratio affects the I-pentane molar flow rate in the tops. So we will go to case studies. We will now add a case study. For this case study, we need to add variables. At least one must be independent and one must be dependent. By independent, we mean that it is a specified value in HYSYS. So we go to the column itself, T101, and here we have all the different variables that we can access. We will choose the spec value because this is where we specified information, and that spec value is the reflux ratio. Note, it comes up as independent because it is information that we supply to HYSYS, hence we can change that information. Next, we will add a dependent variable. And in this case, in the distillate stream, we would like to see the master component molar flow of I-pentane. Note that this is not an independent variable. This is a variable calculated by HYSYS. We need to set the bounds, so we knew that a reflux ratio of 2 as a lower bound worked, and we would like to go up to 8. Note, not all of these reflux ratios may have solutions, but HYSYS will actually find those that have solutions, give us the values, and those that do not have solutions, HYSYS will tell us that there was no solution. We will choose reset after run, seeing it's a distillation column, and we would like to have a fresh calculation after every run. Step 5, we will do steps of 0.5 in the reflux ratio. Now we have set up the case study, we can run the case study. Note it tells you which state it is running, and the total number of states as 13. We can see if there were any failed states, and under the results tab we can get information about the results. We can also look at this information as a plot, and here we see that the reflux ratio varied the I-pentane flow in a non-linear manner. We can see that the lowest I-pentane ratio was gained at a reflux ratio of 2, and the highest being at 4.5. We would like to operate our column with as low an I-pentane in the tops as possible. To do this, we can examine further to this side where the reflux ratio would be lower, although it must stay above the minimum reflux ratio, and to this side where it seems the minimum reflux ratio can eventually be lower. We can go back, change our minimum to 0.5, and we want to look at it in the region of 0.5 to 4, but we would like to look at it much more closely in this region, so we will choose a smaller step size. Next, we click Run, and we shall be traveling through our 29 states. Again, we have no failed states. We can look at our plot, and we can see that at 0.5 we have our very lowest I-pentane. But again, a very non-linear response. Note at all those times the temperature spec of 30 degrees was active, and we were able to get a solution. This may not come without a cost, as our condenser duty and reboiler duty may have changed dramatically in that region. To see those, additionally, we can return to the case study. We can add those variables to the list. So for T101, we have our duty summaries, and we have our condenser duty, which we shall see is not an independent variable, and we shall add our reboiler duty. We must rerun our case study. And now we can look at our results, and we can see that the duty summary for the condenser was higher at the lower reflux ratio. Generally speaking, we would pay additionally for the ability to remove pentane in energy costs or utility costs. We can look at plotting individually the components, or we can choose to remove a plot so the axis can be scaled properly. The basis of this design will determine the financial feasibility, and we will be able to specify whether we want to spend more money on reboiler duty or condenser duty to achieve the separation we require. Note the reflux ratio has changed, and we can place it wherever we need it to be to get the composition we require. In the next video, we'll be looking at the internals of the column, design procedures, and we will be looking also at pump arounds.